Last time we were dealing with Cauchy-Euler equations, and so there's there's a couple more parts that's in this section, that's covered in the section, and one of them is an interesting way to approach this type of problem, and that is to use some sort of substitution to change the way it looks and maybe make it look like something that we've already done before. So we'll start off today by doing some examples of Cauchy-Euler equations where we're going to do a substitution, and then from here we'll look at it and hopefully it'll look something familiar that we can solve. And the substitution is that x is equal to e to the t, your independent variable. We'll change the variables from x to t. So you could view it in a couple of different ways. Either x is equal to e to the t or t is equal to ln x. And then we'll need to change. Remember, the y prime, y double prime, they're all with respect to x. And if we're going to change into t, then we have to change those as well. And so those changes will happen by taking derivatives. Well, let's see if we could take the derivative. So if you have a y prime or dy dx, you want to change that as a function of t. So we're going to assume that x is a function of t. And then take the derivative of this with respect to t. So the derivative of this, or the derivative of y, I guess, with respect to t, since y is a function of x, is going to be dy dx times dx dt. Right? And then dx dt, so what we want to do now is we actually want dy dt, or dy dx, that gets replaced with this, and then well, let's just so if we're solving for dy dx, because that's what we're going to replace, then we can replace it with dy dt times 1 over x. Kind of did it backwards. So we want to replace your dy dx with dy dt times 1 over x. Now the second derivative is a little bit more complicated, because you have to look at dy dt times 1 over x as the derivative, and then you want to take the derivative of that with respect to t. See if I can make this fit into one line. Oh, I'm broken up by equal signs. So when we find y double prime, or when we replace y double prime with this particular substitution, we're going to come up with the y double prime of t minus y prime of t. And then that thing's going to get multiplied by 1 over x. So this is like the change of variable. You know, if we go back to the idea of the use substitution when you do integrals, um, you have to compensate for the derivatives, and so um, we're changing variables again, and this is the compensation for the derivatives. And so what's going to happen here is that your dy or your y double prime is going to get multiplied by 1 over x squared, and then your y prime is also going to get multiplied by 1 over x. And so if you remember the Cauchy-Euler equations, they have they have x squared and they have an x involved for their second order problems. And so um, what happens when you do the substitution is that those variables would cancel. And when they cancel, then it just should look like a second order differential equation with constant coefficients, and we know how to solve for those. Yeah. Oh, this is the actual substitution that you're going to do, and the reason why we're doing this is that so that we can try to solve the problem as if it was one of those problems from section 4.3. Yeah, they're regular. Right. So we're doing the same problem, except this is just an alternate method of doing things. All right, let's try. I'm gonna put this back a little bit higher. Let's try a problem just to see how this actually would work out. 32 maybe. I don't know. Don't say 36. I'm not gonna do that. Oh, for 36, you need 3 derivatives, and so you would need to take the derivative of this second derivative, which is more work than it's worth. So let's do this problem. So we can use the old methods, assuming that your solution's y is equal to x to the m power, and then do all that stuff. But this is just an alternate method, and let's see how this works. So what we say is that we're going to make our substitution, and our substitution is going to involve the derivatives. So these two derivatives over here. And so let's just go ahead and do that. So we got x squared, and then your y double prime is equal to 1 over x squared times d squared y dt squared minus dy dt minus 9x times your y prime is dy dt times 1 over x. And then we have 25, and then you just have your y of x. And then this is equal to 0. Okay. All right. So let's cancel what's supposed to cancel. And the point was that we're expecting that to cancel so that we can rewrite this without the x's. So we have d squared y dt minus dy dt minus 9 dy dt plus 25 y is equal to 0. And now we're going to solve for this differential equation with t's. See if we can remember that. So this is I'm going to write it in the prime double prime notation again. minus 10y prime plus 25y equal to 0. And then now this looks familiar, right? Auxiliary equation. This is your solution, y of t, and remember that it's a t, is e to the m times t. So y of t is m squared minus 10m plus 25 is equal to 0. It's a perfect square, 5, 5. M minus 5 is equal, m minus 5 squared is equal to 0, so m is equal to 5 with multiplicity 2. And so your solutions, and I'm going to keep stressing that this is a function of t, is going to be, what is it, e to the 5t, and then your second solution is what? T times e to the 5t. Okay. All right. So remember. Yeah, we still get, hopefully, still get the same answer, but if you get bored with the other one, it's just the same. It's a different way of solving the same thing. Yeah, so we will get the same results hopefully. And to make sure that we check that, we should probably make our substitutions back. So t is equal to ln of x. So to change this back into y of x, we're going to say so we got y of x now. We're going to write in terms of x is e to the 5 times ln of x. And then what's this? There's some power thing for logarithms, right? We put the 5 up as a power, so e to the ln of x to the 5th. And so your y1 of x is equal to x to the 5th. And then the same thing with y2. It's t ln of x, and then e to the 5 ln of x. So y2 would be ln x times x to the 5th. So if you remember, if we go through the process of doing Cauchy-Euler, the original method that we learned, we'll see that we're probably going to be getting the repeated roots business, and then we'll get the same result. But here goes doing it a different way. Okay. So the key to this is this substitution with the derivatives. So I encourage you to take a look at that and convince yourself with chain rules and stuff like that that those are actually true. All right. Any questions? Speaking of integrals, I told you guys to practice your integrals and stuff. The math club has something happening today. Anybody know? It's an integral. It's like a spelling bee, except it's an integral bee. There's cash prizes. Oh. Mm. So that, wow. Togo sandwiches. Wow. No. I teach from 4 to 7, so yeah. Uh, yeah. So what time is it? The thing? Yeah. So it's a good way to practice your integrals. Um, and I encourage you to go so that you can practice your integrals and get a free T-shirt. Okay. Anybody involved in the math club? Anybody else involved in the math club? Are you guys actually gonna go? Should I give extra credit for this? What extra credit can I give? No. No. So you guys are already getting some extra credit for the next test. How about how about how about for the quiz? I'll, I'll give you I'll give you 2 extra credit points on your lowest quiz that counts. So you guys have quizzes. I dropped the lowest score. So your second lowest score, I'll give you 2 extra points on that quiz if you attend. And so you have to check in with either Chris or Moises, or maybe I should just have you. Okay. So um, make sure you sign in when you go. Yeah, you have to participate, and I want to see the results that you get on this on the integral stuff. I'm assuming you guys are gonna write it down on a piece of paper and submit your answers, right? Can you collect that for me? You're not gonna be there. All right, so I'll tell Moises to, if you want extra credit, you have to submit your integral work to Moises, and he's gonna collect that for me. And then once I get that information, then you're gonna get those 2 extra credit points on some quiz. All right. Okay, so let's move on, and now we're gonna switch sections, move to the next section, and all right. So we have the variation of parameters gives us a particular solution of the form of y1 times some function u1, and then y2 times some function u2, where u1 and u2 were obtained by finding the Wronskian and then the modified Wronskian to use Kramer's rule to help us solve for this. And what happens is that this whole setup can actually be combined and compacted into a simpler. I don't know about simpler, happens to be a handy function to use, and that function that they're going to define is called Green's function. And so if you look at and remember the modified Wronskins, we have like for W1 we have 0 and f of x, and then we have y2 and y2 what prime. I forgot what happens. In any case, because there's a 0 in these modified Wronskins, remember you're going to replace one of the columns with 0 and then the function. With the determinant of this, you're always going to get rid of one of those functions, right? The derivative. And so what you would have left is y2 times f of x. In this case, it would be the negative of that. And then for the W2, we have y1 and y1 prime, and then we have 0 and f of x. And so the y primes, again, get multiplied by 0, and then they disappear. And so we have kind of a neater version without having to deal with those determinants, although they weren't too bad. But we have this extra y prime 1, y1 prime, y2 prime that we never use. And so we can kind of just set that aside. And then from here, we take the integral of this, and then we multiply this by, like for u1, after you take the integral of this, you're going to multiply that by y1. And so that process can be kind of streamlined a little bit. Can be streamlined a little bit into this. There's something weird going on here. So this is U1, and notice that some minor change in the dummy variable inside of the integral. You have U1, and then if we consider the starting point, your initial condition would be your x is equal to x naught starting point, and then you go to some generic x, then we can define a function from your starting point to however far it needs to go. So this whole expression on the right-hand side can actually be, if we combine this into one integral, and then keeping in mind that there's an x, and then the integral itself, when you're taking the integral, has a variable, the working dt, the t variable, then we can kind of put these two functions together into one function that we're going to integrate. So that's how they are going to define Green's function. Oops. So they define Green's function as a function of two variables, the x variable and the t variable, and the t variable is the variable that we're going to use to integrate. And then the x variable is just constant with respect to t, so we're going to leave it outside. And so Green's function can be seen as this thing that we're going to integrate with respect to one of the variables with respect to t, and then our result will end up having x's in it. So what do they do? In here, they just rewrote it, right? So in here, they factored out the f of t, And so you can imagine there's an f of t out here outside of Green's function. And then they put these two together, and then, you know, switch the order or whatever. So it's all the pieces are there. And then it's just a nicer, neater way to find your solutions. So what's neat about this is that we immediately get the solution for your initial value problem. As long as you plug in your values, your x naught into x and stuff. So this is your particular solution. And then you also, this also will help us. I don't know if we're going to have time to do this, but this would also help us solve for boundary value problems, which I think I said that we won't do. Yeah. But on top of that, we won't cover this in this class, but Green's function can also be used to help solve for partial differential equations, and some other types of problems in differential equations that would be that it could be used for. So it's just a good function to know, or if nothing else, you can say that you know Green's function and you know that it comes from variation of parameters, but then you might see it in other contexts as well, like in partial differential equations or some other places. Okay, yeah. Yes. There's a version for like third order, but that gets a little bit more complicated. Okay, so let's see how we can use this now. Oh, let's do a theorem. More information here. So your initial value problem for your non-homogeneous differential equation would look like this, where you have x naught as your starting point. And then the solution, remember, has two parts to it. The solution to the homogeneous differential equation, and then the solution for the particular differential equation. Okay. So let's see if we can use Green's theorem to solve for some of these differential equations. Do I have examples here? Yeah, there's some examples. Let's see. Let's try 2022. Sure. I don't know. I'm not thinking. Yeah. Well, let's do number 22 and see what happens. All right. So it looks like we still have to find the non-homogeneous portion, and then we just find our. So the non-homogeneous or the homogeneous portion of this should be easy, right? Yeah, so it's 3. Can you do this in your head yet? Y equals e to the 3x. Y equals x e to the 3x. All right, so we got y double prime. This is for the homogeneous. 6y prime plus 9y is equal to 0. Your auxiliary equation, m squared plus 6m plus 9. And then so this factors to plus 3 twice. So m is equal to 3 with multiplicity 2. Negative. Thank you. Oh, I was off by negative. So then your y1 is equal to e to the negative 3x, and y2 is equal to x e to the negative 3x. Okay. So Green's theorem. Yeah, I forgot how it looks like already. So Green's function, I mean, so g as a function of x and t over w. Oh, so we need w. So we need the Wronskian is e to the minus 3x, x e to the minus 3x, so minus 3e to the negative 3x, and then e to the negative 3x plus minus 3x e to the 3. Did I do my product rule correctly here? Derivative of the first times the second plus the first, which is x, and derivative of the second is negative 3 e to the negative 3x. So I need to find the determinant, e to the negative 6x minus 3x e to the negative 6x minus negative 3x e to the negative 6x. And I think I'm able to cancel those two. So my Wronskian is just e to the negative 6x. All right, now back to g of x comma t. That means g is a function of two variables, a function of x and a function of t, which is going to be important for us because we need to integrate with respect to t, and so all the x's will be constant. We'll treat them as constants. So we have y1 first with a t, and then y2 and the second one with a t. So that's going to be your way of remembering that. So y1 with a t, so I got e to the negative 3t, and then y2 with an x, and then y1 with an x, and y2 with a t. And then we're going to divide by the Wronskian with a t. Okay? Yeah, we're going to want to simplify it because we're going to integrate it too. So we want to simplify this. So it looks like there's some things that we can work with here. I think this is going to give positive 3t. So e to the 3t times x e to the minus 3x minus e to the negative 3t 3x times t e to the positive 3t. Okay, so that's my function, and I think I'm ready to find my y sub p. And our x naught, by the way, is equal to 0 in this case, so that's going to be our integral starting point from 0 to x. Right? And then the g function, e to the 3t times x e to the negative 3x minus e to the negative 3x times t e to the 3t. And then don't forget your f function as well, written as a function of t. So let's identify the parts. Yeah, because this is just your f of x, right? So this is your g of xt. This is your f of t, and this is your x naught. I think those are the pieces. No, you can split it up into separate integrals and then take out the x's. Yeah. Oh, because f of x, and according to Green's function, this is what we want to integrate. So the best thing to do here is probably to split it up. And so this first term over here, we have two terms, then both of those terms get multiplied with a t. And so let's split this up into 0 to x, and that's t e to the 3t times x e to the minus 3x minus the integral from 0 to x of e to the negative 3x times t squared e to the 3t. And then now we can, the x's are constant with respect to t, so we can move those out. We have x e to the negative 3x times the integral from 0 to x of t e to the 3t. So we're going to need to use, what's that, part by parts for this one, minus e to the negative 3x, integral from 0 to x of t squared e to the 3t. Another integration by parts twice for this one. If you have multiple derivatives that you can get rid of. So let's see, this one, x e to the negative 3x, and then now this business over here is, if you do that u dv business, it's going to be uv, so v is, there's a 1/3 in there, so 1/3 t e to the 3t minus v du. V is going to be the 1/3 e to 3t. So this one requires two of them, so you can't do it in your head, then you can just write it down. You got t squared e to the 3t, 2t and 2, and then zeros after that. The antiderivatives is 1/3 e to the 3t and 1/9 e to the 3t. So this is going to give us a t squared. Oh, sorry. I need to shift all this up. Yeah, so this is e to the 3t start, and then 1 over 1/3 e to the 3t, and then 1/9, and then 1 over 27. It's making me think this should be a 9. Is that true? And then you'd be done. Okay. All right, so back to this business over here. We got 1/3 t squared e to the 3t. This one? Yeah, so you got to take the integral again. So that's why. Yeah. Okay, so this is a 9 right here. All right, so I guess we could have seen that. I mean, u dv t1 and 0 e to the 3t 1/3 e to the 3t and 1/9. So that's a quick way to do your integration by parts. All right, back over here, we have a 2 and a 9. So that's 2/9 t e to the 3t. And then the last one is going to be 2/27 with a positive e to the 3t. And then we want to evaluate this from 0 to x. So usually it's nice when we plug 0 in, everything goes to 0, right? That's not quite the case for these terms that don't have the polynomials, the power functions next to them. So we have to be careful about that. So we're going to put x in there, and then we're going to put 0. So we got x e to the minus 3x. Let's put x in there, so that's a 1/3 x e to the 3x minus 1/9 e to the 3x minus, and then you put 0 in. And when you put 0 into this first term, the t's 0, that whole thing is going to go to 0. But this one, you have 1/9 e to the 0, so this is just going to be a 1/9 negative. So the second term, we got e to the negative 3x, and then let's put x in there first. Got a 1/3 x squared e to the 3x minus 2/9 x e to the 3x plus 2/27 e to the 3x. And now we have to subtract by putting 0 in. And when you put 0, we got a couple of zeros. And then the last one is not 0, 2/27. So I guess we just simplify. When we take this e to the 3x and distribute it, we got a couple of 3x's that will go away. And then this one's going to get that e to the negative 3x. So let's see if we could do this. We got a 1/3 x squared, and then e to the 3x, e to the negative 3x cancel, minus 1/9 x, e to the 3x, e to the negative 3x cancel, and negative negative is a positive 1/9 e to the negative 3x. Oh, x. All right. And then now let's distribute this also. You got negative 1/3 x squared, and e to the negative 3x will cancel. and then a positive 2/9 x, and that stuff cancels, and then negative 2/27, and that stuff cancels, and then now I have another negative, and a negative 2/27 e to the negative 3x. So a couple more things I think would go away. So these are gone. Can we add this? This is just 1/9. And then the constants, there's only one constant term. And then, oh, I can't. There's an x here and there's no x here. Okay. So 1/9 x plus 2/27 negative 3x. Is that what you mean? Okay. So this is our solution, or y particular. We're out of room already. We haven't quite dealt with the homogeneous portion. So we need to continue this on to the next page, looks like. Yeah. Yeah, you can do variation of parameters. We'll come up with the same way, unless I specifically ask you to use Green's function. All right, so we're not quite done with this because according to this theory, we need to find the y solutions to the homogeneous portion of it. So let's continue this. And let's take this information here and our y1 and y2 that we got. So we got y1 equals e to the, was it negative? And then y2 equals x e to the negative 3x. And so our y sub h, maybe we should have done that earlier, is equal to c1 e to the negative 3x plus c2 x e to the negative 3x. And now we're going to plug these initial conditions in to help us solve for c1 and c2. So at x is equal to 0, first we need the first derivative. So this is a negative 3 c1 e to the negative 3x plus, and this is a product rule, derivative of the first times the second plus the first times the derivative of the second. And then let's put in those values. When x is equal to 0, we have y is equal to 1 and y prime is equal to negative 3. So when x is equal to 0, I have c1 plus 0 c2 is equal to 1. Well, that's good. C1 is equal to 1. And then over here, when we put 0 in, we get negative 3c1 plus c2 minus 0, and this is supposed to equal to negative 3. So C1 is equal to 1. And then C2 is equal to 0? 0? So got that. And so our solution, or y sub h, is going to equal to just e to the negative 3x. Okay, combine that with y sub p, whatever y sub p was. That was like long, wasn't it? So we got y sub p from the previous page, and we got y sub h. So let's just combine that with our solution. And this is not the general solution because it's solution to the IVP. So it's actual solution. Y is equal to the y sub h plus the y sub p. Suppose you can combine a couple more things if you want, but I think this is good. So if you were to use variation of parameters, you would have probably got something different on the left-hand side that would make things cancel out. Should we try doing this in variation of parameters and come up with the, we should have done one where we did variation of parameters before. Just saying. It would have. Okay, any questions? Should we try to do another one? Are you guys good with this? Oh, you want to try to solve a variation of parameters? Let's see how we would solve this using variation of parameters. So if we were solving this using variation of parameters, what we would do is we would find our fundamental solution set. So we would get y double prime plus 6y prime plus 9y is equal to 0. And our solution was y1 is equal to e to the negative 3x, y2 is equal to x e to the negative 3x. And then we would solve for the for this using the initial conditions, right? So we'll just go through the steps. I mean, we did it already. So yh equals c1 e to the negative 3x plus c2 x e to the negative 3x. And so we got y sub h is equal to e to the negative 3x. All right, so using variation of parameters, we would say, how do we do variation parameters again? Wronskian, something like that. So W is equal to this, e to the minus 3x. Yeah. So minus 3 e to negative 3x, and then this is some derivative. Put dot 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 here. And then so we need to find y1 and y2, or w1, 0, x, and then x, and then this thing. I guess this still doesn't matter because you're just going to multiply this. Oh, yeah. So, yeah. Because we did it in the previous page. And it's the same work that we would do. Because we're assuming the solution for this is supposed to be the y sub h, where it's a solution to the homogeneous differential equation with the same initial conditions. And so that part is the same. A lot of this is the same. Yeah, so this is what we get after we using initial conditions. Yeah, the h part. All right, the W2 is going to be e to the minus 3x, and then some derivative, and then 0, and then f of x, which is going to be x e to the minus 3x. And so we have W1 that'll help us find U1 prime, and that's going to be minus 2 or minus x squared e to the minus 3x over e to the minus 6x, which is going to equal to negative x squared e to the positive 3x. And then our W2, oh, U2 prime, thanks. Equals W2 over W, which is going to be x e to the minus 3x e to the minus 6x. That would be x e to the 3x. And so we would integrate this. And if you notice, it's going to be the same integral that we had. And then u2 is going to equal to the integral of this. And then your y particular is going to be the y1 times whatever you get for this integral plus y2 times whatever you get for this integral, which is the same amount of work that we've done, except I don't know, this might look nicer because it's nice and compartmentalized and stuff. But I think there's some value in Green's theorem in that it's one of those theorems that can get extended into other things beyond what we're doing. It's kind of like I don't know, for those people that have taken Calc 3. I forgot the example now. thinking about spring break. Oh, calculus. It's like the first derivative test versus the second derivative test. First derivative test kind of gives you everything you need to know, right? And then it always works. The second derivative test is a good test, but it doesn't always work because if the second derivative is equal to 0, then you don't know if it's concave up or down. It could be a maximum, could be a minimum, or it could be neither. So you would think that there's no value in trying to learn the second derivative test, but then when you get to Calc 3, there's no such thing as a first derivative test in Calc 3 because when we're taking derivatives of functions of more than one variable, there's a lot of different ways to get to your critical point. And so in Calc 3, there is a generalization from the second derivative test in Calc 1 to the second derivative test for multivariable calculus. And so there is some value in learning the second derivative test, even though the first derivative test always works. So in saying that, the variation of parameters is all good and well, and it works fine. But then there's this Green's function, which is another alternative to solve the same problem that may seem a lot harder, but not a lot harder. We're doing the same amount of work. But Green's function can be generalized into something that you may or may not get to in the future. But if you do partial differential equations or some other stuff, or if for some reason you're doing some engineering problem and you have to do a boundary value problem, which we're not discussing, Green's theorem, Green's function would be a good mechanism to help solve for those things. Okay. I forgot what I said already. I don't have to do the whole useful. Or, okay. All right. Let's see. Is there anything else in chapter? What chapter are we in? Chapter 4. There's a 4.9. Oh. Oh, yeah, that's the differential equations one. Okay. Yeah, so let's take a look at those. So quiz number 5 is a quiz that you would take in Canvas. If you click on it, it'll be on Canvas. I think you get 2 tries. Or maybe I should. Go to student view. So quiz number 5. Take the quiz, 2 attempts. So you're allowed 2 attempts. Did I say take the quiz? What happened? Oh, there it goes. So it's a multiple choice or true false or something like that. And there's 10 problems to do. And so you do it, you submit it, and then if you feel like you want to take it again, you have 2 tries. So that's the first quiz. The second one, it says go to WebAssign. So you would have to go to WebAssign. However, you get to go. Oh, wait, what does it say? Find the one labeled this, and then you will have 3 chances, and you must submit your work. Take a picture of the work. So if you go to WebAssign, Is this WebAssign? Oh, right here. Here we go. And for this one, there's only 2 problems, but the whole idea is for you to actually do your problem on a piece of paper and show your work. So after you do it, you need to upload a file to submit so we can see the work that's included. Upload file button over here. Oh, I think I said either take a picture of it and save it as a JPEG or scan it or save it as a PDF. So JPEGs or PDFs, yeah. Let's say have it done by Tuesday after spring break. Okay. All right. Good. Have a good spring break. Do your math.